So let's get into it. What is, just explain to all our viewers here, because again, we've never really gotten into it before. Like, what is the Muon G-2 experiment? Why is it so phenomenal, and what does it mean for science?
All right, so let's back up because to
Okay, yeah.
understand this, we need a lot of background.
Let's get the background. Let's get
So
it.
so let's start not with muons but with electrons. So we know from experiments, the Stern-Gerlach experiment, for instance, from 100 years ago, that electrons have spin, and they have spin of plus or minus a half. So this we know to be true. Now, spin, of course, doesn't mean spin in the same way that you think of spinning a ball, but nonetheless, it has angular momentum. So any object that has spin and an electric charge, which the electron does, is also a magnet. And so what we are talking about to start with is essentially how strong of a magnet these subatomic particles are. Now, the G in G-2 is called the gyromagnetic ratio. And so essentially what it is a ratio of the amount of the magnetic strength of a particle divided by what's called the Bohr magneton, which is a thing that Bohr came up with. And in 1935, in classical quantum mechanics, people did a bunch of work, maybe 1938, a little bit older, later than that. People calculated, and G should equal exactly 2.
Exactly.
Numerically,
Okay.
period, 2, 2.0, infinity, nothing.
Nice.
So that was great. But in 1948, an experiment measured the G for an electron, and they found that it wasn't 2, it was 2.00238. So it was a 0.1% difference. So now it would be easy to imagine that if you did an experimental measurement and you got something that was 0.1% off from the prediction, that you just made some sort of experimental error, and the reality is it really was 2, and the 0.001%, it was not 0.01%, but
Yeah.
the 0.1% was simply, you just goofed up. However, the uncertainties on the measurement were much smaller than that 0.1%. So if you believe the uncertainties, it was simply true that the magnetic moment of the electron was not 2, it was 0.1% difference. So it didn't take very long for theorists to think about that and say, aha, you're right, it is in fact 0.1%. And the people that did that, well, first it was Julian Schwinger, but what the people that did all the work eventually shared the Nobel Prize, Schwinger, Tominaga, and Feynman, for the investigation and discovery of quantum electrodynamics, or QED. So what we now know is surrounding a bare electron, there is a cloud of what we call virtual particles, particles that appear and disappear all the time. So you've heard of the Heisenberg uncertainty principle. Things can happen as long as, and not even conserve energy, as long as the non-conservation of energy is short enough. And so what happens, if you look at an electron, you will see that it gives off photons that then make electron and antimatter electrons that then recombine into photons and go back into the electron. But you should think of the electron as like being surrounded by a cloud of fireflies that blink in and out of existence. And so that 0.1% is in addition to the magnetic strength of the electron by the cloud of sort of subatomic fireflies. So when you say, oh, we measure the magnetic strength of the electron, you're measuring a combination of the raw magnetic strength and the cloud addition. So that's kind of the big physics background. Now we talk about the muon. Now the muon is a cousin of the electron. It's 200 times heavier. It does not live very long. It lives 2.2 microseconds, so it's very, very short, at 2 millionths of a second. Luckily, you can use Einstein's theory of relativity to boost it to high speeds, and that will extend its length of being alive a little bit longer. So now we're talking about muon G-2. So to begin with, why do we call it G-2? Well, it's because we're interested in the behavior of that cloud of quantum particles surrounding the electron, or the muon. We're not really interested in what's at the center because that's kind of boring. So G-2 is what you measure minus the boring part, and so what you're left is simply the cool quantum stuff. So that's why it's G-2. So the muon G-2 experiment now studies not the magnetic strength of the electron, but the magnetic strength of the muon. And it is also a similar number. It is about 0.1% different from the 1930s prediction. So if you do that, and we've been doing this for a long time, I think the first measurement of that was back in the 1950s, but over the years we have done a better and better job, and we can now measure the magnetic strength of the muon with a precision of 12 decimal places. 12,
Wow.
that's astounding.
Wow.
And the theoretical calculations are equivalent. And what we find is if you do the 2.00238, blah, 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 they agree, the data, or the measurement, and the prediction agree decimal for 8 digits. And they only disagree in the 9th digit. So this is 1 part per billion where the disagreement begins. Now, to give you a sense of what 1 part per billion is, that is equivalent to measuring the circumference of the Earth with a precision of 30 centimeters, or a foot for my American friends. And so that's how precise this is. Now, once you get past that, they do disagree. And you can, the numbers I'm not going to mention now. If you're actually interested, if you look at the Fermilab YouTube channel, my last YouTube video of about a week or so ago talks about this in great detail. You can actually see the numbers. But for now, we just say that past the part per billion, they do disagree. Now, if you compare the measurement and the prediction, they disagree, and if you look at the uncertainties, they're like, get on the camera here, they're like this. So this might be the prediction, this might be the measurement, and the distance between my fingers is the uncertainty. And you see that the uncertainties don't agree. Now, if they were really, really close, that might be acceptable. And if they overlap, so that the prediction and the experiment overlapped a little bit, you say they agree. Even if they were like this, they might agree. But they're, get the here on the camera, they're like this far away. So this is not cool. They don't agree, and they don't agree within statistical uncertainty or with any uncertainty. And the disagreement is significant. It's essentially 4 standard deviations. So that's...
Oh, wow. That is actually 4 standard deviations. Is pretty heavy.
It is pretty heavy.
Okay.
But it's not the 5 that we do for an observation, but it's very close. So that's the state of the art in 2006. The measurement was done at Brookhaven National Laboratory, which is a sister laboratory outside New York City on Long Island. And so they did an experiment, what we call the Brookhaven Muon g-2 experiment. And everything I've been telling you about is a result of their measurement. Now, obviously what you want to do is you would like to do a better measurement or something. But the problem is that the Muon facility was really tapped out on the amount of muons that they could produce. So it was not feasible really to do anything more there.